Sunspots turn out to be a very important measure of solar activity. So we want to know how many sunspots are there. And so to measure the sunspots, what we do is we have to count them. That's the easiest thing to do. That's how it was done before they had any other kind of instruments, when the only instruments they had were telescopes and eyes. And so they started counting sunspots. They later figured out it's not just the number of spots, but groups of spots turn out to be very important as well. And so they came up with something called the Zurich sunspot number. The relative sunspot number is the number of spots. So each spot plus 10 times the number of groups. So we have the number of spots plus the 10 times the number of groups. That gives you a relative sunspot number. So in the image over here, you see there's like lots of individual spots, some of them very small, but there's several groups of spots. And so what you would do is you count how many groups there are. There's a little group right there too. So you have groups of spots. So 1, 2, 3, 4, 5 groups. And then that would be 50. And then you count the number of spots and add to 50. Now that's the relative sunspot number. What they discovered, though, was that bigger telescopes, you could see more spots. Smaller telescopes, fewer spots. If you were a better observer and more trained, you tend to see more spots. And so they realized the relative number was unique to you and your telescope. But you want to compare that to numbers that other people had. So that's where they came up with something they call an observer factor. And the observer factor turns out to be fairly constant. If you got a small telescope, you don't see enough spots. And so if you see half as many spots as you're supposed to see, then you just multiply your relative number by 2. If you're a really skilled observer and you got a really big telescope, you might see 5 times as many spots as the reference number. And so what you would do is the observer factor would be 0.2. That'd be like dividing by 5. And so that way, different telescopes, different observers can compare their numbers together. It gives an international standard that we call the Zurich sunspot number. So here's a map of Zurich sunspot numbers for the 23rd cycle. And so each one marks like a different month and the average in that month. And so you will go from solar minimum to double solar maximum down to solar minimum down there. Notice that because the Zurich number is number of spots times 10 times the number of groups, if you have one spot on the sun, that would be spot number is 1, but the group number is 1. So the relative number would be 1 plus 10 times 1. So in other words, 11. So the smallest number you can get for a sunspot number is 11. If anything less than that is 0. So 11 is actually the smallest number. The other thing that they discovered after the invention of radio telescopes was the sun actually gives off a lot of radio energy. And so here is a correlation between the radio flux. And so the radio flux, and again, it looks pretty similar to the sunspot numbers. So at solar maximum, the sun gives off more radio waves. At solar minimum, gives off very few radio waves. And this, again, corresponds back here to the 24th cycle, which is just now ending down in here. Okay, there's the sunspot number progression. And that sunspot number progression graph looks almost identical to the radio emission thing. And here's the sunspot number progression for this the last complete cycle, the 24th cycle, and this graph looks almost identical to the previous graph that showed the radio. So there's a good correlation between sunspots and radio emissions out of the sun. That's the radio emissions are really more closely related to solar activity. And so since sunspots related to this, that means that sunspots are actually not a bad measure of activity on the sun. Spots themselves are just symptomatic of something else happening. It's the other things that are happening that we are really interested in. Okay. Again, for the for the last a little over a decade here, 13 years, sunspot numbers. We have the daily numbers plotted in yellow. We have a smoothed average here, rather the monthly numbers are plotted in blue. The smoothed average is the red. And right towards the end of last year, they started making predictions as to what would happen here. And some of the predictions said that sunspots would start becoming more active again. Other predictions said it'd stay minimum for a while. What turns out the later condition is what's happened. The sun has remained in an extended minimum again, similar to the very long extended minimum that occurred in between 2008 and 2010, which was one of the longest solar minima in a long time. That was the minimum between the 23rd and the 24th cycle. So it looks like the minimum between the 24th and the 25th cycle is another really long one. Okay, so as I said, predictions kind of were over a wide range. The lower prediction turns out to be the one that seems to be more accurate. Okay, about the sunspots themselves. Sunspots are actually dark spots on the sun, and they're dark because they're cool. Now, we're cool compared to the sun, so it's still super hot. They're still blinding white hot. They're just less blinding white hot than the rest of the sun, and so that means that the sunspots look a little bit darker by comparison. You dim down the light of the sun so it doesn't blind you, and the sunspots are dimmed down so that they look dark. Sunspots tend to have a darker inner region and a lighter outer region. The darker inner region is called the umbra. The lighter outer region is the penumbra of the sunspot. So here we have a bunch of sunspots here, and the dark umbras are running together, and the penumbras are actually all overlapping there. So you have a big mass of darkness. The lighter darkness is the penumbras all running together, and the dark spots in the middle are the umbras. Just out of side note, if you look down here, you can sort of see some of the granulation in the picture as well. Studying the sun uses some other sort of techniques here. For one thing, we want to measure the magnetic field of the sun. Magnetic field of the sun, you can't just fly a spacecraft up close with a magnet, though now we do have the Parker spacecraft that is doing that, but that's pretty recent. What they realized, though, was Peter Zeeman, a Russian physicist, realized that spectral lines can split in the presence of a magnetic field. Now, this is because in a hydrogen atom or something, you got the nucleus, the electron can act like it's going one way, or the electron can act like it's going the other way. And that makes a little bit different magnetic field for the electron. Electric currents make magnetic fields, so if it goes one way, it makes a magnetic field one way. It goes the other way, it makes a magnetic field the other way. And so that's a little bit different amount of energy. So the spectral lines correspond to different energy levels, but you can have slightly different energies depending on which way the electrons are moving. So the splitting of the spectral lines is a measure of the strength of the magnetic field. And so if you imagine a slit, what we have here on the left is a sunspot group, and that line that runs through there is like running a little slit through there, and you look at the spectral lines along the slit. So down here at the bottom, where the split, where there's no sunspot, the spectral line is whole. But right in the middle here, where you're going through a piece of the umbra of the sunspot, you notice that you have split spectral lines. That tells you the magnetic field is very, very strong in the sunspot. In fact, solar magnetic fields can be amazingly strong. The solar magnetic field can be tens of thousands of times stronger than the magnetic field of the entire sun is roughly the same as the magnetic field of the Earth, but the magnetic field of a sunspot can be tens of thousands of times stronger than the magnetic field of the Earth. In fact, sunspot magnetic fields typically rival the strongest magnetic fields that we produce on Earth by humans. Some sunspots actually have stronger magnetic fields than we've ever produced on Earth. So we can actually measure the magnetic fields of the sun by looking at the Zeeman effect, or the splitting of spectral lines. And that gives us what we call a magnetogram of the sun. So in the left picture, that visually what the sun looks like. On the middle, we see a magnetogram, which is a measure of the intensity of magnetic fields in the sun. One thing you notice is that where the sun is most active magnetically is also where you have sunspot groups, okay, or faculae groups. And so that suggests that the sunspots and the faculae are actually symptomatic of something else, and that's the magnetic field of the sun. And that magnetic field of the sun turns out to be the very important part that determines how the sun and the sun's activity work.